Bon, on va donc reprendre pour la partie séminaire de cette séance. Et donc aujourd'hui, j'ai le grand plaisir que le séminaire soit fait par Michel Ferrero. Beaucoup d'entre vous connaissent Michel, mais l'exercice habituel est de présenter l'orateur, donc c'est ce que je vais faire. Donc Michel est un très grand spécialiste, en particulier des méthodes computationnelles pour le traitement des grands systèmes quantiques, et en particulier des systèmes fermioniques, mais également d'autres. Et pour ceux qui ne le connaissent pas, il a été étudiant à l'école Polytechnique fédérale de Lausanne, où déjà vers la fin de son bachelor, il s'était intéressé aux problèmes de systèmes de spin frustrés, aux problèmes de dimères quantiques, en travaillant avec Frédéric Millat. Et ensuite, il est parti à Trieste faire sa thèse avec Michele Fabrizio. À cette époque, on écrivait même des articles qui étaient un petit peu en compétition l'un avec l'autre, ouais, sur les méthodes de Gutzwiller invariantes par rotation et la transition de mode sélective en orbital. Et donc, à la fin de sa thèse, qu'il a soutenue en 2006, il est venu s'établir en France et il ne l'a jamais quitté. D'abord comme postdoc au CPHT, puis comme chercheur au CNRS. Et aujourd'hui, il va nous parler de simulation de systèmes fermioniques et des défis que représentent ces simulations pour les méthodes Monte-Carlo. Est-ce que les fermions sont nés sous un mauvais signe? Merci beaucoup.
Bon, écoute, merci mille fois, Antoine. C'est vraiment un honneur d'être ici. And I'll switch to English. I'm really glad to be able to talk about modern numerical algorithm to treat strongly correlated fermionic systems. It's a big part of my research, so I'm really very glad that I can share it with you today. So the way I'll structure this talk, at the beginning will look a bit like what Antoine already did earlier. I'll try to motivate why the study of strongly correlated fermionic systems is difficult in general, and I'll try to give you an overview a bit of what numerical methods are on the market and what they do, what are their pros and cons. But then I'll focus in the rest of the talk on a subset of those numerical methods that are belonging to the broad class of quantum Monte Carlo methods and that are based on stochastic algorithms. So to explain a bit how this works, I'll give a quite general introduction of Monte Carlo methods in a very general setup at first, to give you the main ideas and limitations of these kind of approaches. And then I'll talk more specifically about two algorithms that are called continuous time quantum Monte Carlo algorithms that have really played, I think, a major role in solving the equations of the MFT. They've been a bit of a milestone about 10 years ago, a bit more. And so I want to go really there a bit more in the details. Those are now quantum algorithms, and I'll show where this limitation, which is called the fermionic sign problem, comes from, and give you an idea of, well, what is it that we can do and what is it that we cannot do yet. And because we're just between us and there's no founder of DMFT around here, I'll depart a bit from DMFT and tell you a bit about something I'm doing a lot these days at Collège de France, which are diagrammatic Monte Carlo algorithms, which attack directly the models on an infinite lattice, trying to get something like this, and also try to discuss their limitations and how they can be used in a complementary way with clustered DMFT or DMFT approaches in general. So if this was the menu of an Indian restaurant in Paris, you'd get those chili peppers, of how spicy or how much damage to your stomach you might get. And so it will start smooth with just one pepper here, maybe two here. And that last part, I don't really understand it myself. So that's where we'll go. OK, so strongly correlated systems, what's really the challenge? So as Antoine said, in strongly correlated systems, the interaction between electrons leads to very fascinating collective behavior. You get very rich phase diagrams. I just picked one, which maybe I'll talk a bit more later, which is here the one for cuprate superconductors. You see it here as a function of temperature and doping, hole or electron doping. And you see many different phases, exciting ones like superconductivity, which also have maybe, hopefully, someday also some technological applications. So the question is, well, okay, we have these materials. What is it that we can really solve today? And why is it hard? What are the limitations? So rather than going directly for realistic material in all its complexity, as theorists, we like to start from the simplest kind of model that encapsulates the main, or we hope encapsulates the main physics of the problem. That's a bit the spherical cow approach, in which we really take the simplest Hamiltonian. And so a lot of the discussion today will be around the Hubbard model that Antoine introduced. So I tried to find a nice illustration for a spherical cow. I couldn't really get one, but I did find something which is pretty much as close to a spherical sheep as you can get. So that I'm not accused of speciesism, I decided to go for a spherical sheep model here. But you see, even though this is kind of a spherical wool ball, it's fairly intricate, nevertheless. And the same thing is true for the Hubbard model. It's very simple to write, but it has extremely rich physics. And that indeed comes from the competition of those two terms, one which is the kinetic term, which has sort of a natural phrasing in momentum space, and this local interaction term, which is much better understood in real space. So the competition between those two representations makes this actually a very difficult problem to look at. So why is it so hard? And I'm basically repeating what Antoine already said. Well, first of all, there's no analytical solutions except in really a couple of special limits like 1D, and even there, not in its full generalization. And from a numerical point of view, this is hard because it's both a quantum problem and it involves many particles, typically 10 to the 21 or more. And I think Antoine pretty much convinced you that this is difficult. So from a numerical point of view, I try to sort of give you a quick overview of the kind of methods that are around. I'm forgetting many, but this is just a bit of a quick idea. And I try to sort them into two classes, some that I call bottom to top, and others that are rather top to bottom. So what I mean by that is some are more ground state methods. They're aimed at getting the ground state or getting a description of the ground state wave function. And from there, they can build the solution by starting from the ground state and telling you something about what may happen at higher temperatures. So those are in general Hamiltonian-based methods. In some way, they directly try to solve or diagonalize, in a certain sense, the Hamiltonian, and they face their limitation is, as Antoine said, the exponential growth of the Hilbert space, typically 4 to the power the number of states. Or in other methods that try to code the wave function cleverly, like finding a good compression method, if you want, for the wave function, those are limited by the quantum entanglement of the ground state. So the more interactions, the more entangled the ground state becomes, and the more difficult it becomes to find a good sort of compression algorithm for the wave function. So one needs to go through some clever truncations to get something. And even though this is not going to be the subject of this talk, there's a lot of action going on in that direction too, with, well, exactization is maybe the historical one, but density matrix renormalization group, tensor networks, MER-PEPs, there's many of these approaches, and there's still a lot of activity in that direction. Today, I'll more focus on a class of top to bottom approaches. Those are approaches that work best in a regime of high temperature and weak coupling. That's where, if you want, they start from. And gradually, they try telling something about what's happening as you lower temperature or increase the interactions. They're generally based on the path integral on an action-based formulation of the theory. And most of them are Monte Carlo methods. They belong to the broad class, I would say, of quantum Monte Carlo methods. There's continuous time quantum Monte Carlo methods that I'll talk more about. So auxiliary field quantum Monte Carlo, diagrammatic Monte Carlo, Green's function Monte Carlo. I mean, there's a number of them. And they're based on stochastic algorithms. And in these cases, their limitation is something which I will discuss a lot, is the fermionic sign problem. This is what is limiting the extent to which those methods can be pushed to low temperature, strong interaction. Okay? Sure.
Is there a reason why you put the arrows?
No, there's no reason. I just didn't want, no, of course, I just want to say basically from something which is not too correlated, which looks quite a bit like a Fermi liquid, to the places where you have more phases, more correlation effects. That's basically what I'm trying to represent here. Okay, so what I just described here are methods that can attack the problem directly on the lattice, but this morning Antoine introduced the dynamical mean field theory, so this should be simplifying the problem. So how simpler does the problem become as I introduce the dynamical mean field theory? So again, to repeat what the dynamical mean field theory is, it basically maps or approximates the Hubbard model, which is defined on an infinite in principle lattice, to an atom, just a single atom, which is embedded in an environment, an electronic environment, with which it can exchange electrons. So you basically have one, in the simplest case of a single band Hubbard model, you'd have just one electronic level with those 4 possible states, empty, spin up, spin down, or double occupied level. And it can exchange electrons with an electronic bath. And that exchange is described, the way this exchange is possible, if you want the dynamics of the electrons, is described through a function that is called a hybridization function, and that function encapsulates the structure of the bath, and it is also the function that is set self-consistently within the DMFT equations. Okay? Good. So actually, this is called an Anderson impurity model, and before DMFT, there has already been quite a bit of interest into Anderson impurity models, very much in the context of the Kondo problem. So there have already been methods that have been developed to try to attack this problem, but DMFT, I would say, introduced a new set of requirements on your wish list for a good impurity solver, which were not necessarily very important at the time when people were trying to understand the Kondo physics. So the wish list as a theorist for a good impurity solver, for a good method to solve this Anderson impurity problem, would be something that says, okay, I want something which is sensitive to all the structure at all energy scales of the bath. This is an important ingredient in the DMFT equations, and it's not something that is necessarily so easy to get from a numerical algorithm. One wants to be able to treat generic Hamiltonians. In the simplest version of DMFT, this is just a single level, but as you go to the description of realistic materials or to more sophisticated models, you may want this to be a multi-band model with Hund's coupling and this kind of more generic Hamiltonians, or to go to cluster extensions of DMFT where you have several atoms instead of just one here. You want to be able to be quite flexible in the temperature regimes you can access, and to the best situation, you'd like to have something which is numerically exact. So that's a tough wish list, and it is certainly simpler to get such a solver for an impurity model than for the full lattice, but it's still a very difficult thing to do. Okay, maybe one thing I want to say about why it's still a difficult problem is that, of course, it's just a single atom, but it's embedded in an electronic environment, which itself is described by an infinite number of degrees of freedom. And from the moment this correlated impurity starts talking with the electronic bath, this correlates the full system. So this is still a system which has an infinite number of degrees of freedom. What maybe happened is that instead of really having a two-dimensional system, you can represent that impurity problem as a one-dimensional system if you were to think about it in a Hamiltonian way. So in a sense, the simplification is that I went to a one-dimensional system to a certain extent. So Hamiltonian approaches work better there. There are cases in which they can be very efficient. The two difficulties they maybe face is that it's a bit more difficult to say something about finite temperature. They're a bit better aimed at zero temperature. But mainly, in my view, their limitation right now is rather the way they scale with the number of orbitals, the number of sites you include. So they don't scale so well with increasing number of orbitals. Anyway, what I will rather talk about is another set of approaches, which are these continuous time quantum Monte Carlo algorithms. Like I said, they appeared in 2004, 2005, more or less. And I think they've really been a bit of a revolution with respect to what was on the market before this. There's different flavors of these algorithms that I'll describe. And they have been successful in addressing multi-orbital, strongly correlated materials, and, for example, to go to cluster extensions of DMFT. And I think those were the two things that really appeared with those new algorithms that was really difficult to do before. And like I said, they're based on a stochastic, on a Monte Carlo method, and their limitation, as I will discuss, is the fermionic sanctuary. So to try to give you a taste for what this means here, I'll try to give you a really quick introduction to Monte Carlo methods, but really very much in general to give you, a taste for these kind of approaches. I know many of you are specialists in the field, but this is aimed at someone who maybe is not doing this every day. So the way to give you a taste for Monte Carlo method is, well, how can I use a statistical method? So how can I use a probabilistic method to try to compute something? And the simplest example one can maybe think of is this experiment in which we want to try to compute pi, the number pi, through a stochastic process, through a stochastic experiment. A way you can do this is, imagine you draw on the floor a 2x2 square, and inside that square you draw a circle of radius 1. And you start throwing stones in that region, and you try to do this, it's hard as a human being, but to do it uniformly with no bias over the full square. If you do this and repeat this experiment many times, you can look at the ratio of stones that fall inside the circle, and you compute the ratio between what's inside and the total area, multiply by 4, and this will give you an estimate for pi. So let's do this experiment and see how this actually gives me an estimate for pi. This is the number of stones I'm throwing, and this is the estimate for pi. You see quite quickly I get at least the 3 correctly. It's not so bad. But after 100 throws, you'll see it's quite hard even to stabilize the first decimal here. After 100 throws, this value for pi is quite far still from what I would want. So I need to throw more stones. So let me throw more stones and go a bit quicker. Now the stones are much smaller, fainter dots here, because otherwise one wouldn't see anything. So it's gradually getting redder and redder. And you see it takes, well, a good 30,000 or 50,000 throws before I get the first decimal right. The second decimal starts to stabilize around, well, probably more than 50,000. And very slowly, I stabilize. Actually, I don't stabilize it for this number of throws, but very slowly I start to get better statistics for that last decimal. So the message is, yes, statistical methods can compute things like pi, but definitely the experiment needs to be repeated many, many, many times. So let me try to formalize this mathematically a bit more clearly in this way. So this experiment, basically what it represents is a random variable that describes a single throw. This random variable can take two values, 0 or 4. 4 if it falls inside, so that happens with probability pi over 4. And 0 if it falls outside, and this happens with probability 4 minus pi over 4, 1 minus pi over 4. And of course, its average value is pi. Of course, that's what we expect for this random throw. Eventually, its average value is pi. But what is the typical deviation I get for a single throw away from pi? So I can compute the variance of this random variable. I'll skip the math. And you see the variance is huge. For a single throw, the variance is something like 1.64. So on a single throw, I get an estimate of pi, which is very, very wrong. This is not going to help me so much. So what's the trick to get something better? Well, the trick is to repeat this experiment many times and do an average over many repetitions of this. So basically to introduce a new random variable, which is called an empirical average. It's an average over many throws. And if you do the same math here, well, of course, its average value is also pi. But the error bar, the uncertainty on the result, as you repeat the experiment many, many times, decreases. And it decreases like 1 over square root of n. So that's how your uncertainty on the result decreases with number of throws. So you see, it doesn't go down so quickly. So you can actually check this and do the experiment for many different number of throws. This is a log-log plot here. And you see to decrease the error bar by a factor of 10, you need 100 more times. I mean, you need to throw 100 times more. Okay? So that is going to be a bit the limitation in these statistical approaches. So very often we refer to statistical approaches like this to be numerically exact. So they're numerically exact in the sense that there's no approximation in this way to compute pi, at least formally speaking, in the limit of an infinite number of throws. But nevertheless, this comes with a statistical error bar for a finite number of throws. So it's controlled, but that's something one has to keep in mind. Okay. So that was a very simple illustration to compute pi, but quite generally, Monte Carlo methods are methods that give you a way to compute integrals. So let me write an integral here. I'll do it in one dimension to make things easy here. So the integral is an integral of some function, f of x dx. For now, I'll suppose that f of x is a positive function. And I'll decompose this integral in the following way. I'll cut it in two pieces, a rho of x, f of x divided by rho of x, such that this rho of x has the property that, well, it's a positive number, and that its integral gives 1. The reason I'm doing this is I want to interpret rho of x as a probability density, right? So you see, by doing so, I can interpret that integral here as the average value of f of x divided by rho of x over a distribution rho of x, okay? So if I were able to throw or to choose x randomly in a way that it follows the distribution rho, I could get an estimate of this integral by computing the function, by summing over my different throws or my different random values for x, the function g of x, which is f of x divided by rho of x. That would give me an estimate for my integral. So the challenge is, how do I actually get to produce randomly values of x which are distributed according to a law that I want to choose? How do I generate x's that are distributed according to rho? So the way to do this, I mean, there's actually different ways, but one way that we use a lot to do this is to generate a Markov chain. So a set of x1, x2, x3, then x4. So I produce one value after the other in a clever way that I'll describe in a second. And this Markov chain eventually describes the variable x distributed like rho. And one way to do this is to use something which is called the Metropolis-Hastings algorithm, which is probably one of the key algorithms that has been developed in the 20th century. So I couldn't resist putting a slide about it. So I'll describe this later. Anyway, suppose you're able to do this. Suppose you're able to distribute your variable x according to that distribution. You can use Monte Carlo to try to get an estimate for the integral. So the stone example, to try to put it in this framework, was, well, basically the integral of a square of a probability distribution which was uniform on the square, which was 1/4, times a function g of x, which was, well, f of x, which is 1, divided by 1/4, so either 4 if I'm inside the circle or 0 if I'm outside the circle. So that's how I can rewrite the previous example in this language. Of course, this can be done now a lot more generally for any kind of function. Imagine that blue function here that you want to integrate. And the question is, okay, now I have a freedom in the probability distribution rho that I will choose to try to get an estimate for the integral. And that's an important notion when you use Monte Carlo methods. I could, of course, try to estimate this integral by using a uniform distribution, a bit in the spirit of the stone experiment, and throw random numbers completely uniformly on this interval. But this is actually quite an inefficient way to do it, because many times you'll get those green dots are just like a given set of points that were chosen according to a uniform law. And you see many points fall in places where the function is essentially 0. So in a sense, these throws are useless because they don't sample anything useful of the function. So you want to choose rho, this probability distribution, in a way that the points you pick randomly are close to where the function is actually important or has a lot of structure. So for example, a much better distribution would be, for example, a Gaussian law here around 0 like this, so that the points mainly sample the structure of the function where it's important. So that's an important notion. It reduces, if you choose rho of x well, it reduces your uncertainty on the final result. And this is something which is called importance sampling. So choosing a good distribution here is key in the development of those Monte Carlo methods. Okay? So like I said, I cannot resist, well, I'll go quickly. Saying just one word about the Metropolis-Hastings algorithm. Probably heard about it many times. So the question is, well, I want to draw points, x, according to a given distribution. So in the jargon of Metropolis, we call these x, we call them configurations because they can be in a multidimensional space. They can be more than just a number. They can be anything else. So again, the strategy is to create a Markov chain. And the way you do this, you start from some random configuration, random number, and then you propose a new one with some chosen probability. So you have your own strategy on how to propose that new number starting from x1. This is anything you choose. So you choose this probability p of x. And then this new configuration, this new number y, you either accept it or reject it. So the Metropolis-Hastings algorithm is called an accept-reject scheme. So either you keep that or you don't keep it, but you do this with a well-defined acceptance probability, which is given by this, the minimum between 1 and this fraction here, which only involves things that you know, the probability distribution that you want, and this probability that you chose here. And if you do that, so either you accept the move, and if you accept it, the next configuration, the next number x2 is going to be y, or you reject it, and in that case you remain, you just keep x2 equal to x1, you stay in the same with the same number. Okay? And you can show that if you do it this way, eventually your distribution here of these points will follow rho. So that's a very powerful and elegant algorithm. And that's typically how it's implemented in a code, but don't mind this. So statistical or these stochastic approaches have been and are still very powerful to study classical statistical physics systems, and I'll try to motivate this by taking the example of the Ising model. So this is defined on some lattice. You have a set of spins at different lattice sites I. They take either value +1 or -1. And for example, here they interact through some exchange J, which can either, according to the sign of J, favor two spins being in the same direction or in opposite directions. You can also put a magnetic field term which favors one direction of the spins. And so this is classical physics. So if you want to compute some average quantity, it will, for example, the average magnetization, it will look like this. It's the sum over all possible realizations of spin configurations on the lattice of your Boltzmann weight, which is e to the minus beta, the energy of your configuration. So beta is the inverse temperature here, times the magnetization of that given configuration. And you have to do this sum over all configurations and divide by the partition function. Now this is a classical problem, but it's not an easy one. There's still 2 to the power n such configurations. So if you actually want to do that sum explicitly, this is completely impossible for large enough lattices. So Monte Carlo is a good way to try to tackle this problem. You can naturally rewrite this average value as a sum over all configuration of some rho, which is going to be my probability density rho of c times mc divided by sum over c of rho of c. And rho of c here, if I compare, is going to be my Boltzmann weight, e to the minus beta h, the energy. And what I have to accumulate, the function, is just the magnetization. So there's a very natural choice in statistical physics for the way to cut this integral if you want. There's a very, very natural weight that comes out here and gives a nice probability, and it has the very good taste to be a positive number. Okay? So this is very efficient, and stochastic approaches have been very successful on many different statistical physics problems. But as you go to quantum systems, there is no longer such a natural way to cut the integrals you're facing. And More importantly, the typical weight you will get here, or the thing that appears instead of the Boltzmann weight, is going to be something which doesn't necessarily have a positive sign. So this is going to be the issue with quantum systems. So, is this a dead end? Does it mean that whenever the function I'm trying to integrate is not positive, there's no way to do it? Well, actually, in principle, no. I can very easily generalize the approach I was describing to a case of a function which is alternating in sign. Of course, I cannot define a probability distribution which is negative, but what I could do is take a probability distribution, for example, that would be the absolute value of the function times some coefficient here to normalize it. Okay? So I can do this, and for this function, for example, sample the points according to the distribution rho, which is just the absolute value of the function. This is still going to sample the function basically where it's big in absolute value, right? Now the only difference is that the object you're sampling now, the function that you have to sample, well, it is a positive number here and a negative number here. So it's basically going to be the sign of the function, well, times the inverse of this normalization constant. So basically you will have to sample by Monte Carlo a function which is alternating in sign like this. Now, this is more difficult in a sense that typically because now this function alternates in sign, it will have a big variance around the final result. You see, the final result of this integral is this orange line, which is a fairly small number. And I will have to get this from an integration of a function which has a big variance around this average value. So this is more difficult. But it's not, in that case, there's no reason why it would be impossible. It just means that I start from a variance which is larger, and I will have to make more steps before I can actually reach the result. So that's a sign problem in I would say, classical Monte Carlo. It's, of course, it makes your life a bit more difficult, but this is not exactly the same sign problem as the one we'll meet in quantum systems. In quantum systems, the real difficulty will be that those oscillations here of the function, the amplitude of these oscillations, or the variance of the function around its average value, will grow exponentially with the parameters of your systems, for example, with lower temperatures, with beta, or with the system size, or with the interaction. And this is really the fermionic sign problem. It is the idea that you have to integrate functions which have large variance, and actually a variance which increases exponentially with, for example, inverse temperature and so on. Okay? So that's about it for this brief introduction to statistical methods. And now I'll try to really switch now to true quantum Monte Carlo algorithms, focusing on continuous time quantum Monte Carlo algorithms that have really been very useful in a setup of dynamical mean field theory. So this part is a bit more involved. Especially, I'll try to derive really the steps of the algorithm. Again, what I want to solve is an Anderson impurity model. And all these approaches, quantum Monte Carlo approaches, are generally based on an action formalism or on a path integral formalism. So the way to represent your problem or to compute, say, your partition function is a path integral over your fields, d dagger, which are the ones that create spins on your impurity level, of e to the minus some action. Okay? So the action is something that will look like this, which describes the system. This is, if you want, the equivalent of the Hamiltonian in a path integral or in an action-based formalism. And you'll recognize basically the two kind of terms you have on this impurity model. There's the local interaction term, which is u and up and down. This is the interaction on the level. And there is another term here, which describes the physics of the exchange of electrons between the impurity level and the electronic bath. Again, an exchange which is described by this hybridization function. So this function g here, g0, this is, if you want, the Green's function that describes the system with no interaction. It has several pieces, one of which is this hybridization function, which again describes the structure of the transition of electrons. So this is really the dynamics, if you want, of destroying an electron on the impurity, putting it in the electronic bath for some time, which is given by this function. It describes its dynamics in the bath, and then at some point it comes back on the impurity. That's the interpretation, if you want, of this term. So these are the building blocks of the action and of the way to compute the partition function. So continuous time quantum Monte Carlo methods appear in several flavors, 3 of them, I'd say, with names CityInt, CityHib, CityOx. So the CityInt is the first one that appeared. It's been developed by Alexei Rubtsov and Sascha Lichtenstein. It's called the interaction expansion approach. A couple of years later, Philippe Werner and Annie Millis proposed the hybridization expansion. And then there's also another one, Emmanuel Goul, Olivier Parcollet, and Matthias Treuer, which is called CityOx, the auxiliary field formulation. So those 2, it turns out, are very similar in the kind of problems they can address. The equations are a bit different, but they really do more or less the same thing, and especially their interaction expansion-based algorithm. So they basically try to start from the non-interacting system and try to systematically construct the perturbation series in the interaction U. That's what these guys do here. So they're trying to build up the perturbation theory in U of your model. While this one takes the opposite limit, which in a sense is more in the spirit of DMFT, which starts from the atom and takes this hybridization function as the perturbation. So it builds up a perturbation theory, but this time in the hybridization, if you want, in the hopping between the impurity and the bath. Okay? So I'll spend more time explaining this one, which is a bit simpler, but the other ones are very similar in spirit. Okay? So they're all based on stochastic methods. So let me check my time. Okay, good. So let me go through the equations here without going through all the details, but nevertheless try to give you a taste for what is going on. So the idea is to construct a perturbation series. So the point is to take your action, which had those 2 pieces, and cut it into one piece, which will be my starting point. This is, if you want, the system with no interaction. This describes the system as if U were equal to 0. And then there's a perturbation, which is the term which describes the Coulomb interaction on the impurity. And what I want to do is to try to treat this perturbatively. So I cut my reaction into these 2 pieces, e to the minus S0. This is my non-interacting system, and this is my perturbation. And I'll just write this term as a Taylor series. It's an exponential, and I write this as a Taylor series. So I get something which is something like this. Maybe just let me say one more thing. If this part here, if you want, is a path integral over that action, which is the action of the non-interacting system. So what is really written here is actually the computation of the average value of this second term here, but taken in the non-interacting value. So if I want to write this partition function, what I have to do is compute in the non-interacting system the value, if you want, of this exponential of minus SU, which is this interaction term. So I do a Taylor expansion, and what I get is something like this. My partition function is a sum. This, you recognize the Taylor expansion of the exponential. And the exponential has, in SU, you have those integrals over time. So at a given power n, you'll get n times those integrals that fall down. So you'll get n integrals between 0 and beta. And you'll have n times those operators n up and down that fall down in your expansion. And you need to take the average of those different operators in the non-interacting system. So that's basically what you have to compute to get this perturbation series. You see it's a perturbation series in U, so it appears with powers of U here. Okay? Now, how do I compute this average here? Well, it turns out that this is the average in a non-interacting system. So this, you can actually use Wick's theorem to compute this, and this you can express simply as some determinant. Forget about the details, but that's basically just a determinant you have to compute. So eventually you get some expression like this for the partition function, which is a big sum and many integrals over imaginary times of a determinant times minus U to the power n. So it's a very large sum, as you can see. I mean, this is a multiple integral here, so it's quite natural to try to compute this by Monte Carlo. So I rephrase this in the language of Monte Carlo. I will this sum over n and over imaginary times, I'll call this a configuration. These are all the kind of numbers or configuration I have to draw statistically. And they have a corresponding weight, which is going to be this thing here, the determinant times this. Okay? So in the Monte Carlo setup, I want to define a configuration, which would be the set of n and all these imaginary times that we often represent like this. It's a string of vertices between 0 and beta. So at order 5, it would maybe look like this. And I want to stochastically sample these with something related to this weight here. Except this weight here, as you can see from the minus, is not necessarily positive. So we'll have to take, just as I did before, the absolute value of this thing. So in the computation of a typical observable, like density, which would have a formulation which reminds very much the one for a statistical classical system, I will have to pick here as a weight the absolute value of omega, the absolute value of this number here. Okay? So the price to pay when I do this, just as before, if I formalize it, to get an average value of an observable, I will have to statistically accumulate something which involves the sign of this weight. And this is something which is going to oscillate here as a function of n. And this is what leads to the fermionic sign problem. So you can show, and I'll show this in the next slide, that the variance, the typical variance of this function here is something that goes exponentially as a function of n and as a function of inverse temperature. Okay? It is getting a bit more technical, you might have noticed. So let's try to get an estimate of the typical amplitudes that contribute to the partition function. So what are the typical amplitudes that are sampled? So if I look at this function, it's something that goes, you can show this, essentially as u beta, beta is the inverse temperature, to the power n divided by n factorial. So if I look at this as a function of n, this will typically have a distribution like this, with the main contributions will come from a maximum which is located at orders which are proportional or close to beta u. Okay? So the typical contributions at that maximum perturbation order are going to be of the order of beta u to the power beta u divided by beta u factorial. Okay, and this you can show that is something that actually goes like exponential of beta u. So the main contributions that enter your Monte Carlo process, the main amplitudes that enter your integral, are contributions that typically oscillate over amplitudes that are exponential in beta u. And they have to sum up to something which is of order 1, or at least something which is not exponential. Okay? So this is really how the fermionic sign problem appears in this continuous time Monte Carlo algorithm. As I will try to reduce the temperature or increase u, the variance of my typical amplitudes that are sampled will become exponentially big, and eventually this will make it impossible to reach the desired accuracy. Okay, this is a bit more technical, but I felt this was useful. In practice, the way we implement this kind of algorithm is to start, again, doing this with the Metropolis hostings procedure. We start from some random configuration, and then we propose new configurations according to two schemes. Either we add a new vertex randomly somewhere, and this we propose as a new configuration that we either accept or reject, or we decide to remove one of the vertices and then go to a lower perturbation order, and again, either accept or reject this. Okay? And we do this repeatedly. You can show that this is ergodic and eventually should converge to the exact answer. So, that's the fermionic sign problem. So is it really completely impossible to get to any low temperatures because of this exponential scaling? Well, it turns out that, again, rather than going brute force, sometimes thinking a bit more about the problem can actually help you a lot. And Optique had the great idea to use a freedom that we have in the way we write the Hamiltonian. So right now, I started from a Hamiltonian that was written as un up and down. But he figured that, well, we can also write this by introducing a variable alpha in that way. I mean, if you do the math, those two things are exactly equivalent. So I have a certain freedom in the way I write the interaction Hamiltonian by introducing this artificial alpha. And it turns out, I'm skipping the math here, that by cleverly picking alpha, you can greatly improve the sign problem. You can improve it so well that for single orbital models, you can actually completely get rid of the sign problem. And you can get to a formulation where every single weight is positive. So it's really quite nice. And so by tuning this, it really allows to make quite significant progress in single orbital models for sure, but also in multi-orbital cases or in cluster extensions of those impurity models. So to sum up, the complexity comes from computing the determinants. This is of order n cubed, okay? And the typical perturbation order, like I showed before, is something that goes like beta u. So that, those two things together tell you a bit how the algorithm scales. So you'll see the perturbation orders, this comes from an actual simulation, go up as temperature goes down or u goes up. And the sign problem is exponential.
Sorry, can I ask another question?
Yes?
Can you explain again why you can add this alpha?
No, if you look at those two things, they're exactly the same. Right? If you do the math, this is like a u n up, and it comes with a minus alpha, so there's a term minus alpha u n up, and it cancels with these terms u alpha n up. So if you just develop this term, you'll get exactly this by putting the right constant here, which depends on alpha. But it's just a constant. So those are the same things. I just introduced it artificially. I introduced an alpha, which changes a bit the way I write the Hamiltonian. And by doing so, the way I write my perturbation series is a bit different now, because my interaction vertices are a bit different, so I have to introduce counter terms and so on. So basically, the determinants here that appear are a bit different, and they depend on alpha. And by cleverly tuning those alphas, I can reach a situation where those determinants have exactly the same alternation as this. So they compensate every time the minus. So they come with a minus 1 to the power n as well if I pick alpha cleverly in single orbital cases. If I go to more general problems, like multi-orbital problems, there is no such alpha that will always work, so it helps me up to a certain point, and then as I go to lower temperatures, eventually I start having a sign problem again. Okay? Yes, Julio?
Can you tell us, is there a simple argument of why, how you can choose alpha in such a way that the sign
I can, but it would take a bit of time. It turns out that the alpha has two effects, sorry. One effect is to help your sign problem, and it also changes the typical average perturbation theory you're sampling. And one thing which is maybe more intuitive is to understand how alpha is changing the typical perturbation order. Actually, by cleverly picking alpha, what you're really doing is writing the perturbation series around a different starting point. And if you pick alpha cleverly, you can, for example, start from the mean field solution of the theory, the static mean field solution of the theory. And when you do this, if you want, this is the best way to sort of include correlations at the non-interacting level, if you want. And then this typically reduces your perturbation order. And at the same time, it can help your sign problem. Okay. So in a sense, the way to understand it is this gives you a freedom on your starting point of the perturbation. Yes?
Could one use alpha and beta if we have some symmetry? And the second is alpha is somehow connected to the average filling of fermions?
Alpha is connected to the average filling?
Yes.
Yes, in a certain sense, yes. So just the way I said, so a good starting point is mean field, and in mean field, the interpretation of this term is going to be the average value of those operators. So alpha is, in a sense, definitely related to the average value of the number of operators. Is it a function of beta? Well, not so much. I mean, I would not...
No, sorry, I don't want to say beta is wrong. Because if you have a thermomagnetic situation imbalance, then alpha will be not the same.
Oh, you mean, oh, sure, sorry. Yeah, to make this simple, I did not intro. Of course, you have more degrees of freedom, so you could make alpha spin dependent, indeed, and in general you do. No, sure. So sorry, my bad. No, you're perfectly right. So you can generalize this and put alphas that are spin dependent, and it can help in spin imbalance cases, for example. Yes, you're perfectly right. Okay, great. I'm almost halfway through my talk. So here, without going really in the details, the hybridization expansion algorithm is really based on the same idea. I'm not giving you any details, but the idea now is to cut the action in a way that you have the local action, so the action of your atom, and the perturbation, which is the hybridization to the base. And the concept is exactly the same. You cut your action in these two pieces, and you do a Taylor series in the hybridization. And you see the formulas are a bit more intricate here, and especially one thing which is different is earlier when I was computing my terms, I was computing these terms in the non-interacting state. But now I start from the atomic limit, so it means I have to compute those averages in the atomic limit. Okay, so there's no Wick's theorem anymore, and to compute the typical terms that appear, I will have to compute a trace over the internal states of my atom. So typically the weight of the partition function is now something which involves, thanks to some symmetries, again, some determinant, and a trace of a string of operators on my impurity. Okay. So again, those contributions in principle have alternating signs, but again, it turns out that for single impurity, for single orbital models, there's no sign problem. It appears as you go to multi-orbital systems. And again, the complexity of the algorithm is essentially goes, again, you have to mainly compute determinants, so it goes order n3. And the average perturbation order this time doesn't scale with U, because you start from the atomic limit, so it rather scales with the average kinetic energy. So the more kinetic energy you have, the higher you have to go in perturbation orders in the hybridization, which makes some sense. Now, when you go to multi-orbital systems, you still have to compute those traces, and the Hilbert space grows. So eventually, as you go to the larger number of orbitals, eventually the bottleneck will become the computation of the trace. And so this hybridization expansion Monte Carlo cannot deal with a very large number of orbitals. So to summarize, and I'm happy I made it this far, there has been really a very important, I think, step in this in solving the DMFT equations with these continuous time quantum Monte Carlo algorithms. They come in sort of two groups, and they're quite complementary. Interaction expansion-based algorithms are better at dealing with many orbitals or many atoms in your impurity cluster. They're good at weak coupling high temperature, but they're facing more difficulties at low temperatures or in going to more generic Hamiltonians like a Calamari. The CT-Hib instead is very good at taking any Hamiltonian because you start from the sort of the diagonalization of the impurity, so you can put any Hamiltonian in there, and it goes pretty nicely to low temperatures. However, it doesn't scale so well with the number of orbitals. So putting those two things together gives sort of two complementary approaches, which have been really useful. So many models, as Antoine said, have been investigated. The Hubbard model, Holstein-Hubbard, Kondo lattice, things that have retarded interactions. I mean, many different things. They've been essential in allowing to go to extensions of the dynamical mean field theory, like DCA, CDMFT, dual fermions, Trilex, D gamma A, whatnot. I think they've also really been an important step in the computation of realistic structure calculations for strongly correlated materials within the DFT plus DMFT framework. And let me mention that there are also, out of equilibrium generalization of these algorithms, there are stunning, I see Laura here, that are being developed. Okay, check the time. So two applications really briefly to show you a bit the state of the art. One of them is those methods for single orbital models can be pushed so far. They're imaginary time methods, so they provide information on the imaginary time axis or in imaginary time frequencies, but you can reach accuracies which are so good that you can actually do analytical continuation here using Padeo approximants that is quite stable, and that here compares very nicely with methods like NRG, which work directly on the real axis. And this is, for example, a comparison of a self-energy for a beta lattice calculation, which is really agrees well with NRG. This is for a simple Anderson impurity model as a function of temperature, where you can really see that you resolve and build up the Abrikosov-Soule resonance here very nicely. Another example, but here just very quickly, we've been able here with Emmanuel Goul and collaborators to really go to extensions of DMFT where you, instead of solving a single orbital, you start solving clusters of orbitals, and you have a systematic way to get more resolution in your self-energy. And this has allowed us to say something about the way you enter the Mott insulator as you go from the metal into the insulator by lowering the doping. And it goes through several stages of Mott transition that first make the antinodal region insulating and then eventually go to the node. Okay, in the times that's left, one can ask, well, you know, those look like very successful methods. Why could I not just take those algorithms and try to go directly to the lattice, not do DMFT, but just look at the lattice problem? Well, in the case of the hybridization expansion, it's quite obvious. I mean, this thing starts from the atomic problem. If you start to increase it to a larger lattice, you'll obviously face the exponential increase of the cluster. And so this is not going to be the best method to do this. For the interaction expansion algorithm, the thing is a bit more delicate, and what kills you there is extensivity. What you sample in this interaction expansion algorithm is the partition function, and the partition function is an extensive quantity. So as the system size increases, because the quantity is extensive, you will go sampling higher and higher perturbation orders, and to make a long story really short, the average sign, or your sign problem, is going to get worse and worse. Now, to go a bit more in the details, so far I've carefully avoided to talk about diagrams because I didn't want to go into those details, but I think here it's quite interesting. The problem really stems from the following. When I sample the partition function at a given order, when I compute my determinant, this is really what I'm doing is really summing the n factorial diagrams of my perturbation theory. And so there's a full family of diagrams that I'm summing, and there are some diagrams which are disconnected and some diagrams which are connected. The connected diagrams are those that contribute to intensive quantities in your system, the physical quantities that you're interested in. And then there's a large set of other diagrams which are disconnected, which don't have a direct intensive meaning, they're extensive. And the point is that as you go to large orders, those diagrams that are heavy are completely canceling the signal of those connected diagrams. So basically, it's a bit of a frustration when I compute an order 50 diagram with my determinant. I actually compute the sum of all these guys, but the information that comes from these intensive guys which carry the physics of the system is completely erased by those disconnected diagrams. So even a small error bar on the final sum here is a large relative error bar on those diagrams that participate to the physics. So the way to go around this is called diagrammatic Monte Carlo, which is an approach which this time tries to directly go to the lattice, and I'll try to be quick here. So the idea is to sample directly the physical quantity of interest, say the density or the grid function, and write a perturbation theory in U. But this time by only sampling the connected diagrams. Okay? So it's hard to find easy expressions for this part which is only connected. So originally, what was done is to actually sample one topology, one connected topology after the other, which was proposed by Svistunov and Prokofiev. And that was the first approach. And there's basically two challenges in those approaches. The problem is obviously the fermionic sign problem again. So when you try to compute those coefficients, those different topologies may have alternating signs, and so this induces a sign problem. But there's a newcomer in the field, which is the resummation of the series. While the partition function, the series for the partition function was a well-behaved series because the partition function is an entire function in the coupling, those physical observables are in general not entire functions. They have poles in the complex plane of U, and so that makes it hard to resum. So there's a new difficulty, which is how do I actually resum this series with the knowledge of a finite number of coefficients. So there's been a lot of progress, and here I'll go really quickly. One has been a way to sum up all those connected topologies at once by using determinants through a recursive formula. But this turns out to come at a fairly high cost, which is an exponential cost, goes like 3 to the power n. But that turned out to be really an important step to improve the accuracy and the computation of those calculations. And we can typically now compute 10 to 12 orders. Other progress that has been made is in the way to resum those series. So like I said, if I take a physical quantity like the density seen as a function of U in the complex plane, this will typically have poles in the complex plane. And this defines the convergence radius of your series. So if you want to evaluate the series away, outside this convergence radius, well, you have to do something about it in a way or another. So one approach is to, there's a full literature in the 60s about how to do clever maps to try to evaluate the series outside the convergence radius. Another approach that we've also been using is, again, using some freedom, very much in the spirit of what I said earlier, introducing a different starting point. And by doing so, we could show that for a physical, here it's a self-energy, by tuning alpha cleverly, we can change the structure of the series in the complex plane in a way to put the poles outside the radius of where you want to evaluate your series, and this is a way to improve the resummation.
Yeah, Michel, maybe you can explain the movie a little bit more.
Yeah, I'm infinitely late already, but okay. Sure, so I can explain that movie again. So what this movie shows is this is in the complex plane of U, so this is real part of U, imaginary part of U. It shows this is the self-energy at the first Matsubara frequency, that's say the quantity, the physical quantity you're interested in, okay? And I compute this, but from different starting point of my perturbation series. So my starting point is I have a freedom on starting from different non-interacting propagators, and this freedom is encapsulated in a variable alpha that I can tune. So if I change alpha, I change my starting point, and therefore I change my series, and therefore I change the structure of the self-energy in the complex plane. And that's what you see in this movie is different peaks for alpha, different values of alpha, different non-interacting propagators, and they change the pole structure of the self-energy in the complex plane. Now this red dot is where I eventually want to evaluate my series. So I really want to evaluate the series at this point. So you see in the beginning, there are poles that are closer to the origin than this point, so there's no hope I can resum the series. But as I tune alpha, I can make these poles go further than the actual evaluation point by tuning alpha well, like here, for example. All the poles are further away than the evaluation point, and my series is convergent. Okay? So one has to cleverly choose alpha, and again, it turns out that the optimal choice generally for alpha is the one that describes the starting point, which is mean field theory. This is the one which tends to put the poles furthest away for reasons which I have to say I don't quite understand.
Sorry, what would be mean field value in this case, for example? Because in a sense that there is no interaction, so which mean field...
I mean, this is just the starting point. So of course, there's also a part which is the interaction, which has a U. So this is, typically the value of U that I'm interested in is here about, 3 maybe? Okay. And again, you'll see that the optimal value for alpha is the average value of the density at U equal to 3. That is what pushes those poles furthest away, more or less. I mean,
so this is kind of the renormalization of chemical potential if you change Hubbard interaction in...
Yes, in a sense, that renormalizes the chemical potential, just the way static mean field does. No, I mean, it depends what you mean by optimal. Of course, if you really go extremely carefully, it's not exactly that value, but it is so that it's always quite close to the static mean field value. At least it's a good guess. I mean, then it might be a bit around it, but it's almost always a good starting point somehow. Okay. So let me summarize here, and I think that will probably be my last slide. So this method the main message is that they really allow to tackle the infinite lattice directly. So there's no approximation as far as the lattice size is concerned. You can go directly for a study of the infinite lattice and focus on some physical quantities. It comes at a price. So unlike the other algorithms, which were cubic in n, those guys go exponentially, so the numerical price to pay is harder. But we can get 10 to 12 orders in the Hubbard model. So there's finite convergence radii, so we have to think a bit how to resum the series. But it has allowed to find some solutions in interesting regimes of the Hubbard model. So there's a lot of ongoing efforts to try to generalize this to different models, to find even better starting points. And one which we're quite excited about right now with Fedor Shimkovich is to try to start from a G0, which is itself a function of U, but in a more sophisticated way than just static mean field, something that really has more information about the final answer. And we've already had quite successful results for the atomic limit and are investigating this. Okay, I think I'll have to stop here and try to conclude about where we stand with fermions and where they're really born under a bad sign. So the way I thought about this title was actually listening to this beautiful tune that you maybe know from Albert King, who was a blues singer and guitarist. And funnily enough, the cover of this album has already 2 of the main ingredients of the Schrödinger cat experiment. So maybe unconsciously, Albert King was aware of quantum mechanics. But it's a typical blues song, so it kind of has a pessimistic vision of things. And the hard luck and trouble is my only friend. If it wasn't for bad luck, I wouldn't have no luck at all. So is this really the situation we are facing when we try to get new algorithm for the fermionic systems? I tend to have a more optimistic or more positive note, a conclusion about this. I think they are indeed very challenging, but there's been great progress in the past 10 years in these systems, and I'm sure there's even more to come. I think those quantum Monte Carlo methods are playing an important role in this progress. They've really led to important progress within the dynamical mean field theory, and they are starting to provide really exciting results in the infinite lattice limit. We can reach the pseudo-gap regime in the doped Hubbard model, for example. We can essentially solve the weak to intermediate coupling half-filled Hubbard model. This work by Ferrero, Szymkowicz, and Kozik. So it's really starting to be quite promising. And so if fermions were born under a bad sign, I hope that those developments on the theory and on the algorithms are going to be their lucky star. With this, I'd like to acknowledge all these people that I had a chance to collaborate with on these issues. There are some usual suspects. You probably know this guy. Olivier Parcollet, I've been working with for so many years. Alice Moutnet, Thomas Schaeffer, Weibu, Zhenya Kozik, Fedor Szymkowicz, Ricardo Rossi, Yaksha Vucicevic, and Alfred Kirsch. And with this, I'd like to thank you for your attention, and sorry about the time.